stabilized asymmetric porous composites for thermal electrification. So to understand this research, we need to know what is actually thermal electrification. Basically, thermal electrification is the flow of heat in a particular direction, wherein the flow of heat is blown in other direction. It is similarly like an electronic diode, where electricity is flow in a direction and blown in other direction. So as we are moving to we are moving to global carbon reduction. So efficient thermal management studies are no longer optional, it's very urgent. For example, like keeping the site stressor pool or protecting our satellite vehicles, which is very necessary for thermal management strategy. So what is the challenge? That is actually fabricating the asymmetric material structure that is highly challenging. And what is the limitations of the current methods that are available to create these kind of structures? Traditionally, scientists do PCM, which is chain materials, for this kind of symmetry, create these kind of structures. But they are very, they have major flow, like they have risk of leakage, and they are also very limited to specific narrow temperature ranges. Also, the other methods like gradient diffusion or laser bonding often suffer from high cost and insufficient thermal asymmetry. So all these limitations brings us to our solution, that is MS particles. Named after a Roman god which has two faces. You can see the picture in background. MS particle basically has an amphiphilic nature. One side is hydrophilic side, which is silica part, and the other side is hydrophobic side, which is polystyrene side. So what it actually does, because of this split personality, it has incredible stabilizer. So when we make water in oil emulsion, these MS particles stuck themselves at the interface and act as a mechanical armor around the water droplets. So what it does, that it provides us to formation of pores, and which enables us to create highly asymmetric materials, which enable us to achieve the efficient thermal rectification. The next part will explain for you.
Now I will explain the fabrication method. So first we will form the emulsion, did an N-type acrylate with genus particles in a glass bottle, and then we will add water with drop ice. And after adding the water, we mix it strongly so that the water droplets breaks into smaller droplets. And the genus particles, since Bhavani has explained that it has two properties, that it has it has two parts, the hydrophilic part and the hydrophobic part. So hydrophilic part get attached to the water molecules, and hydrophobic part get attached to the monomer, that is N-butyl acrylate. And the genus particles prevents the water droplets from getting merged, and so it makes a stable emulsion. Here we found two types of emulsion by varying the concentration of genus particles. So now for casting the layers, again we will take a new glass bottle, and then we will pour emulsion A into the glass bottle, and so it forms this. So it will form this bottom layer, and then we will pour another emulsion, and that will form this top layer. And since at this stage these are in liquid phase, so at this stage the boundary here both the layers get mixed slightly, so these layers get stick together strongly. Now after casting these two layers, we seal the glass bottle and put and heat it at 70 degrees Celsius for about 24 hours. And on heating, these are monomers, and these after heating these get polarization. These get polarized, so it will get solidified, and after getting solidified, but the water is still there in the droplets. So after getting solidified, we will take out from the glass bottles, and we will heat, we will dry it on a convection oven, so that until all the water get evaporated and we get here porous structure. So finally we get a asymmetric porous structure. Now I will explain the characterization of this. So here you can see that it is the inner microstructure of the top layer, and the circular spherical droplet shows the porous side, and this it is the inner microstructure of the bottom layer. And this image shows the orientation of the genus particles. So here these are the void area, vacant area. So since the genus particles has two parts, hydrophilic and hydrophobic, so the genus particles or the hydrophilic part is on this void side, on this side, that is void side, and the hydrophobic polystyrene part gets embedded into the polymer. Now this image shows that there is no clear actual boundary between the two layers. Here you can see that in this image. Now this image shows the pore size and the porosity of both the layers. So here this one shows the average pore size of the top layer, that is about 160 micrometer, and it shows the pore size or average pore size of the bottom diameter, that is bottom pore, that is 140 micrometer, and it shows the porosity. So it shows the porosity of the top layer, that is about 76%, and it shows the porosity of the bottom layer, that is about 60%. Now the Ajit will explain the further part.
So now moving on to the experimental and simulation part. So basically, there is a hot plate which is at 100 degrees Celsius, and we have two different cases. First one is the forward direction case, in which the smaller pores are in contact with the hot plate, and the second one is the reverse direction, in which the larger pores are in contact with the heat plate. So this is the experimental part. As we can say, initially both are at the same temperature, but as time passes on, nearly like 200 seconds later, there is a significant difference of more than 2 degrees Celsius. And this is the simulation part of this experiment, which matches with the experimental data. This is here the data is plotted with respect to time and the temperature, and as we can see, after certain duration of time, its kind of saturates. And this part shows the simulation at a particular time, which is at 1 second. And this is for the reverse, and this is for the forward. So, like my friend already explained, it is acting like a diode. So basically, we can optimize it based on our needs. Like we can change the pore size, or we can change the porosity depending upon the requirement. So basically, here three different kind of combination, and here is the pore size and porosity depending upon these three categories. Okay, and as we can see from here, as the porosity ratio increases, so does thermal rectification ratio. And we can extend this idea from single layer to multi-layer by repeating smaller pores and larger pores. And this is the same image of this multi-layer structure. And this is forward sequence, larger pores initially, and this is the reverse sequence. And it was found that as the number of layers were increased, so the temperature difference, and which means the thermal rectification was improved.
So far we understand about the thermal rectification process. So now let's see how we can apply this in real life. So actually they formed a bilayer sheet in 30 cross 30 plus 1 centimeter dimension, and that is flexible enough and tough enough that don't break after this. And they also make a small house kind of model to measure the temperature inside it. So they add also a thermocouple inside. Also they take 4 cases. One is keep it completely blank. Another is keep the sheet on it such that the small pore side is on the outer side. Next is large pore side in the outer case, and another one case is taking only large pore combination, uniform large pore combination with same thickness. So यहाँ पे क्या होगा ना, if we take this case 2, this is in forward condition at the daytime, then the heat will be accumulated fast in the daytime, so we can flow through this and come inside the room and make the room hotter. But in this case, this is in reverse condition state, so heat cannot, they block the heat accumulation, so slow accumulation rate. But at the night, what happens now? At the night, the room temperature is high and the environment is low. So in this case, that is in reverse condition, so heat cannot go outside that much. But in this case, that heat can go outside, but and keep it more cooler. Next slide. So they keep the house model for 36 hours and take the readings. At the day, the readings in temperature is quite high, but at the night the temperature is low. So let me show the June. So this is the June. This is the June image of the pink part and the blue part. At the daytime, you can see the sensor 1, that is the normal room temperature, that is in black color. Red is the sensor 2, green is sensor 3, and blue is sensor 4. So from comparing the red one and the green one, you can easily see this shows the thermal electrification behavior. And on the other hand, at the night, this gives the opposite behavior. This proves the thermal electrification behavior in our daily life. So, in conclusion, we can say that genus particle mode composites overcome the limitation of PCMs like leakage problem and the temperature reasoning. Also, it has high thermal stability up to 300 degrees centigrade. Low conductivity that make these composites ideal for protecting equipment in deep space situation, and optimize the smart building efficiency by dynamically managing heat flow during